All right, today I just want to continue with some more examples of the word problem type questions that deal with taking derivatives implicitly, where we take the derivative with respect to a variable. Usually time is the variable that we'll be concerned with. And so the first example, I have it up here on the overhead, talking about crime rate. Now, notice the initial problem, the equation has capital T's and C's in it, and it says C is the number of crimes, T is the average monthly temperature. Okay? But as we read through the problem, notice what the question is asking. And this is how you know that you need to do implicit differentiation. It says, how fast is the crime rate rising at the end of the month? Now, when we talk about a crime rate changing, okay, what would be the independent variable? What would be the thing that that we want to check how the crime rate is changing, but wouldn't the independent variable be the amount of days or the amount of months or whatever? It's going to be some time component. It doesn't say how fast is the crime rate changing with respect to temperature. It doesn't say anything about, if the temperature changes, then tell me how the crime changes. Okay? So since it doesn't specifically say to relate to this other variable, we can pretty safely assume that time is really the independent variable. Okay? All right, so that's our clue on how we know that this question is supposed to be solved with time as our independent variable. Okay, now let me put the question up here on the board, the formula, and then we'll go ahead and work through it here. T minus 60 quantity squared plus 100. All right, I want to take the derivative with respect to time. So what is the derivative of this with respect to time? What's the derivative of C? Just 1, right? And then I have to multiply by dc dt. Now, I got a couple of different t's in here. This capital T will stand for temperature, and then this lowercase t will stand for the time component. Okay? All right, so the derivative of C with respect to time. Okay. What's my derivative of all of this right here? How do I take the derivative of something like this? Okay, I have to do a chain rule, right? Okay, first of all, the 2 comes out front, so 2 times 1/10 would be either 2 over 10 or 1 over 5. T minus 60 is now raised to the first. And then with the chain rule, what is the derivative inside of here? The derivative of T is just 1. But now remember, we're doing implicit here, so what do I need to multiply by? dt, right. Okay, d capital T over d lowercase t. The change in temperature over change in time, right. Okay, yeah, so I had a derivative in here was just 1, but then I had to multiply by dt. Okay, so that takes care of the first part. The derivative of 100 is just 0. Okay, so this is our derivative. Now, the only things we have to sub in. The question was, how does the crime rate change? So this will be the thing we're trying to solve for. We need to have a value for temperature, and we need to have a value for how the temperature is changing. Okay? And as we look back at the information over here, what's the temperature that they care about? 76 degrees. Okay? So we'll sub in 76 for the temperature value. And how much is the temperature changing? 8 degrees per month, right. Okay? And so I would sub that value of 8 in for the change in temperature. And now it's just a matter of doing the calculation here. 16 times 8 divided by 5, whatever that comes out to be. Okay? That will be your answer. And what that is really saying is this. Okay? First of all, what is time in this problem? As we were reading through here, what is the unit of time? It's in months, right, because our 8 degrees over here was 8 degrees per month. Okay? So what this is saying is that when we're really close to the month of May, if we let a full month go by, we should expect the crime rate to go up by this much. Okay? And now, is there any good reasons why the crime rate should increase around May or June or somewhere in there? Well, what's usually happening to the weather? Well, the weather's getting a little warmer, so more people are outside, so maybe that's the reason why the crime rate goes up. If we were doing this problem and we were around December, then we would expect probably the crime rate would be a negative number. We would expect the value to be going down because it's colder, people aren't outside committing crimes. That would be my guess on what the reasoning is here. Okay? Just as I look at this problem, it appears that 60 degrees is kind of the magic number. Because if I get any temperature less than 60 degrees, won't this be a negative value? Okay? And then my crime rate will probably be going down. So it appears that they think 60 degrees, anything warmer than that, there's more people outside, probably more crimes being committed. Okay? All right, so there's one example. Not really a difficult example, but I just want to point out as you're reading through the word problems, what is it about those problems that tells you that you need to take the derivative with respect to time? Okay? And so hopefully I've illustrated that on this example. Okay? All right, let's look at another one here. Okay, I want to do number 14. There it is. Okay, let me give you a chance to read it here. All right, company is increasing production at the rate of 25 units per day. The daily demand function is determined by the fact that the price is a linear function of Q. At a price of 70, the demand is 0. 100 items will be demanded at a price of $60. Find the rate of change of revenue with respect to time when the daily production is 20. Okay, key thing that I notice as I'm reading through all this stuff is the last sentence. Find the rate of change of revenue with respect to time. So to me, that is saying that by the time I get to the end of the problem, this is what I want to solve for. Change in revenue with respect to time. So I want dr dt. Now, as I set up my equation, that is my clue that I need to write some type of a revenue equation. I need to have an R equals equation. And I'll get that from all the rest of the data that's provided. Okay? All right, so if we go back and look at the specifics here so that we can generate this revenue equation. Okay, second sentence, the daily demand function is determined by the fact that the price is linear. So we need to write a linear equation for our demand function. Okay, it says at a price of $70, the demand is 0. So I have an ordered pair. $70, demand is equal to 0. And 100 items demand a price of $60. Okay? And over here, this is my dollar amount. Okay, so this is like my price function. Okay, lowercase p we used for price earlier this semester. And this value over here, whoops, did I do that backwards? Let's see. At a price of $70, the demand is 0. Okay, so that's right. I think I flipped these two, didn't I? And 100 items is a demand of $60. Yeah, so I flipped these two numbers here. That's my mistake. Okay, so good example of why we want to go through and label things. Okay, because I just made this silly mistake there. The price is now $60. Okay, and over here, this would be like our Q variable. This is our quantity. This is the number of items that we're talking about. Okay, so they want us to write a linear equation that relates these two ideas or these two together. Okay, well, what are the two things I need to know to write a linear equation? Got to know a slope and I got to know a y-intercept, sure, or some other point on the graph, right? Okay, so let's go ahead and do that. Let's write this equation. Okay, Q equals, all right, now, what is my slope? How much did the Q value change? 100. And how much did my price change? Okay, and now I'm looking at it from this one to this one. So negative 10, right? Okay, since we went up 100 here, we went down 10 right here. Okay, so it looks like my slope on this function is negative 10. Okay, all right. Now I'm going to back this up here a little bit. The second part of writing an equation is that we have to know some ordered pair within that equation. Okay, just like we write equations of tangent lines, this is the same thing. Okay, I've got my slope. Now my ordered pair, I can pick either one of these two. So I'll let the p value be 70, and I'll let the q value be 0. Okay? All right, so here's my linear equation. Q equals negative 10 times p minus 70. If I want to go through and multiply it out, I can have negative 10p plus 700. All right, so here's my equation. Now, here's the question that I really need to ask you though. Okay? How do we take an equation that relates price and quantity, how do we take that and turn it into a revenue equation? Okay? And we've done a few of these over the semester. Okay? But the idea for a revenue equation is you take the number of items that you sell, which is Q, times the price that you charge for those items. Okay? Usually we said X times P of X. Well, here we just called our X as a Q, so Q times P of Q. Right? Now, the only problem with this is this equation is really not solved for P. And so I need to kind of go back and do a little bit of algebra and solve this equation for P. You know, had I been smart and looked at this ahead of time, I might have just written this equation the other direction and I wouldn't have had to do this. Okay, but I didn't notice that right away. So let's go ahead and solve this. Okay, I subtract 700 and divide by negative 10. Okay, and now I've got an equation which is P in terms of Q. Okay, so this function right here, this will be the one that goes in for P of Q up here. So my revenue is Q times Q minus 700 divided by negative 10. Okay, this is my revenue equation. And this is why I wanted to do this one together in class, okay, so that we could talk about, you know, remind you of how to set up a revenue equation. Okay. All right, now at this point, my goal is still to find dr dt, and I think I'm pretty close now in being ready to actually calculate that derivative. I think what might be easier, just go through and let's multiply some stuff through so we don't have to do a product rule when we take the derivative. Okay? If I multiply this times this, okay, I get a q squared, and then I've still got this denominator divided by negative 10. Okay, I'm going to split this apart into two separate fractions. Okay? And then I'll have a plus sign because I got negative over negative. 700 divided by 10 be 70. 70 times q is 70q. Okay? And so this is my function. And this will be a lot easier to take the derivative of than if I was to leave it here and have to do a product rule. Okay? All right, now let's go ahead and take the derivative. What if we got to this point and I gave you this as your test question and I said find dr dt off of this? Okay? Would you be able to do that? All right, well, what's the derivative of the left side? Just dr dt, right? Okay? What is the derivative of this thing right here? Okay? My first question is, well, what do we do with this negative 10? If stuff is ever multiplied or divided, right, we just kind of keep it there. Okay? So we can kind of think about it as a negative 1/10 and just kind of leave it off to the side. Now what's the derivative of q squared? 2 times q. And since we're taking the derivative with respect to time, what else do I need here? dq dt. Right. Okay, so that takes care of that problem. What's the derivative of 70 times q? 70. And what else do I need? dq dt. Right. Okay. Everything's got some type of a rate of change attached to it because we don't have any functions, we don't have any t variables in here, so we're going to have all these dr dt's and dq dt's. Okay. All right, now we need to go back to the problem and start figuring out, we need to figure out a value for q and we need to figure out a rate of change for q. All right, so how many items are we looking at here? $20 items, yes, very last part there. So this is 2 times 20 here. And what is our rate of change? How is the quantity changing with respect to time? 25. It says in the first sentence, the company is increasing production at a rate of 25 units per day. Okay, this is units. This is days, and so that's the dq dt. All right? So this will be 25. This will be 70 times 25. Okay? And it just becomes a matter of punching this in your calculator, and you can figure out what the result is. Okay? All right, so that was a little more difficult example there. Okay? Now, not all of our implicit differentiation questions are they're not all revenue or business type examples. We also have some in the physical sciences. And I'm going to go ahead and do number 26 right here as our next example. Okay? Talking about a rock thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle increases at a rate of 2 feet per minute. Find the rate at which the area is changing when the radius is 4. Okay? Now again, just like I did yesterday on the first example, we're going to solve this, or at least look at it, investigate it a little bit, just in terms of logic, and then we'll jump in and show how the derivative also gives us that same answer even faster. Okay? All right, what are the things that we know about this problem when it starts? Okay, well, the question at the bottom says, find the rate at which the area is changing when the radius is 4. So we start out with a radius of 4 on our circle. Okay. Now, what is happening to the radius when that rock hits the center point? How is it changing? It's getting bigger by how much? 2 feet per minute, right. Okay. So this is the initial value that we'll start with, is when the radius is equal to 4. If we let a full minute go by, now how big is our circle? Now our circle has a radius of 6, right. So let's just go ahead and start with that. Let's go ahead and find out how much has the area of the circle changed from the initial instant to 1 minute later. Okay? All right. So what's our formula for area of a circle? Pi times radius squared. Okay? So this is our initial value, or initial formula that we need. Okay, how big is how much area does the initial circle take up? Well, the radius is 4, so we just sub it in, and I'll put a sub 4, meaning that the radius is really 4. Okay, just to remind ourselves that's what it is. Or I could do it this way, a of 4. Okay, so radius squared times pi is just 16 times pi. Okay, all right, what if we go to 1 minute later? Okay, how big is the circle now? 36 pi, sure. Okay, 6 squared times pi, so 36 pi. So how much, what is our dA dt? How much change in area do we have versus change in time? Okay, well, how much change in area did we have? 20 pi, right? Okay, we increased by 20 pi. And how much time elapsed? 1 minute, right. Okay, so our change in area over change in time is 20 pi, and this is, what is it, feet? Yeah, so feet squared per minute. Okay, so this is our label, 20 pi feet squared per minute. Really don't need that equal sign. Okay, now let's start looking at this if we shrink down the time component. You know, what if I don't let a whole minute go by? Okay? What if we cut this back to just a half a minute? So just 30 seconds. Okay? Now, what are the two values that we need to compare? We need to compare the original value of 4 with what? What if only a half a minute goes by? Well, then it's only going to be up to 5, right? It's only going to increase by 1 unit. Okay? So if we only let 1/2 of a minute go by, so 30 seconds go by, okay? Now we've got a of 4 is 16 pi. A of 5 is 25 pi, 5 squared times pi. So now how much is this value changing by? What's our dA dt on this one? Well, how much did the area change? 9 pi. And how much time elapsed? 0.5, only a half of a minute, right, because we want to keep our label the same. We want to keep it in minutes. Okay, so 9 pi divided by 0.5. Okay, dividing by 0.5 will be the same as multiply by 2. So the answer this time is 18 pi, feet squared per minute. Okay, so as we continue to do this, and this is just like what we did yesterday, you know, if we continue to let this time interval get smaller and smaller, what is happening to this value? Well, here it was 20 pi. Here it's 18 pi. Any guesses on what the answer should be if we actually go like from 4 to 4.01? What do you think it might be getting close to? If this pattern continues, here's 20 pi, Here's 18 pi. What do you think the value would be if we got really close to 4? Maybe close to 16 pi, right? Because if this went down by about 2 pi, it's a reasonable guess that the next one might also go down by about 2 pi. So we think that the answer, if we just let the time interval be really, really small, and that's what this question is after, okay? It says find the rate at which the area is changing at the instant it is 4. So if we let the time interval be really, really small, we think the answer should be close to 16 pi. Okay? Now let's see if calculus gives us that answer. Okay? All right, go ahead and erase some of this work. Here's our initial formula to start with. We want to take the derivative with respect to time on this problem. So what is the derivative of the left side? What's the derivative of a? dA dt, right? It's just a 1. Notice I'm not even writing the 1s anymore. It's just 1 times dA dt. Okay? What is the derivative of pi r squared with respect to time? Now remember, pi is just a number here. Okay? 2 pi r, and then dr dt. Good. Okay? So here's the calculus. We've now got a dA dt in the problem. That's good because that's really the value that we're after. Only two things I need to know is a radius and I need to know a change in radius. Okay, well what's the radius that we care about? We care about what's happening right at the instant when it's 4. So I sub in 4. And then how much is the radius changing? At a rate of 2 feet per minute, right. So I sub in the 2 here. And guess what I get when I multiply all this together? 16 pi. Okay? So yes, we were correct in our guess that this answer looks like it's getting really close to 16 pi. Okay? All right. I show you a lot of this other stuff just so you can kind of see what's going on behind the scenes, that you get an understanding of what this is really measuring. You know, what are we trying to find out? Well, we're finding out that if we just let just a really small time interval go by, how much bigger is that area each minute? Well, it gets this much bigger each minute, about 16 pi. Okay? All right, so there's one example of a physical sciences application. Let's do one more example with physical sciences. Okay? This will be a volume question. This time we'll just go straight to the calculus and let it do the solving for us. Okay, it says a sand storage tank used by the highway department for winter storms is leaking. As the sand leaks out, it forms a conical pile. The radius of the base of the pile increases at a rate of 1 inch per minute. Height of the pile is always twice the radius of the base. Find the rate at which the volume of the pile is increasing at the instant when the radius is 5. Okay, as I go through, and there's lots of stuff there to decipher, but the first thing is, what are we trying to solve for? Okay, we're supposed to find the last sentence. Find the rate at which the volume is increasing. Okay, and so we're probably trying to solve for dV dt. How is the volume changing, or how is the rate increasing? Okay, so we need to have some type of a volume equation, and then we'll take the derivative with respect to time. Okay, that's always the first thing I try to identify, because that gives me a clue. Okay, I need to write some type of volume equation. Now, we've got this conical sand pile here. Okay, as it's, we've got this auger over here or whatever that's just dropping this out and it's forming a nice little cone here. Okay, what are the things that we need to know to find the volume of this cone? Okay. Well, they tell us in the problem, they tell us something about the radius, and that's probably a reasonable thing. We have to know the radius to find a volume. And then the other thing is we have to know what the height is. Okay? And so if we know those two components, then we'll be able to find this volume. Now, what does it say about how the height and the radius are related in this problem? The second to last sentence there, height of the pile is always twice the radius. Okay? So if this radius is 5, the height would be what? Would be 10. So what if it's just a radius of r? The height would be what? 2r. Sure. Okay? So this will be one thing that helps us is by subbing in a 2r there for h, and then we've eliminated a variable. Okay? All right, now, off to the side, You know, if I gave you this for a test question, I would give you the formula for volume. Okay, I don't expect you to memorize all these different geometry formulas. Okay, the formula for the volume of a cone is pi r squared, which is the area of that circle on the bottom. Then we multiply by the height of the cone, and then we multiply by 1/3. Okay, so if I gave you this formula, now the question would be, could you finish the problem from here? Okay, and hopefully the answer is yes. Okay, what's probably the first thing we want to adjust on this formula here? Okay, make the h a 2r, right? That'll get rid of that extra variable, sure. So if we sub in a 2r in here for the height, and then kind of clean this up a little bit here, what would be the formula for volume? I'll bring it up over here. If I take 2 times 1/3, I get what? 2/3. I've still got a pi, and I've got r to the what? Cubed, right. Okay, so this is a much easier formula. Okay, so we made that substitution, we cleaned it up. Now let's take the derivative with respect to time. Okay, from here it should be pretty simple because it's actually a pretty easy derivative. What's the derivative of v? dv dt. Okay, all right, the derivative of this side. Again, 2/3 is just a number. Pi is just a number. Okay, so I'm basically just taking the derivative of r cubed. 3r squared, right. Okay, so I've got this 2/3, I've got this pi, and the derivative here is 3r squared. And then what else do I need here? dr dt, sure. All right, now I could have multiplied these two together, and in fact I probably want to do this now. What's three of these 2/3? That's just 2, right? So if I clean this up, I get 2 pi r squared dr dt. Okay? Again, the only two things I have to know a value for the radius, and I have to know a value for how the radius is changing. What are those numbers? Okay, radius is 5, that's the number we care about, and how's it changing? At a rate of 1 feet per minute, right? Or 1 inch per minute, sorry. Okay, so 2 pi, 5 squared times 1. Okay. Plug all this in, we get 25 times 2, it looks like it's 50 times pi. Okay, what is the label for this 50 times pi? Okay, well the label comes from over here. Okay, what's the label for volume in this problem? All of our dimensions were in what? Inches, and so the label for volume would be inches cubed. And what's the label for time in this problem? Minutes, right. Okay. So what this is saying is that the volume is changing at a rate of whatever 50 times pi is, so that's about 150. So 150 cubic inches per minute. That's how the volume is changing. Okay? All right. Questions with any of these? I never have given you the name of this concept that we talked about here, but what we've been doing the last couple of days, the name of this concept is called a related rate problem. Okay? And what they mean by related rate is if we know one of the rates, if we know how the radius is changing, can we solve for how another variable is changing? Okay, so we're looking at this rate compared to a different rate. And yes, we know how to solve that because we have implicit differentiation. Okay, so related rates is the name of this concept. Okay. All right, questions with this? All right, very good. All right, we'll switch gears here to another concept which can be mentioned in two different words. Whoops, an R. Sometimes they are called differentials, okay? And other times they are called linear approximations. Okay? Now, what I want to start with is I want to start by doing a linear approximation, and then I will show you how calculus can be used to solve a problem a little bit faster using this concept of a differential. Okay? All right. It's going to take a little bit of work to set this concept up, though. Okay? All right. Let's say, for example, that we have a graph. just x versus y, and let's just look at the square root function. Y equals square root of x. Okay? Square root of x graph starts at 0, and then it has some type of a curve like this. It just goes off to the right. Okay? All right. What happens is that as we get to more and more advanced functions, as we get, this is a pretty basic function, but if we got to a more advanced function, okay, what they find out in the sciences is that a lot of times, instead of actually calculating an exact value off of a function, what if I want to know, say I want to know the square root of 1.03, okay? Well, yeah, we've got a calculator that can do that, but if it's a lot more complicated function, it's not as nice to be able to calculate these types of things. And so what we will do is, instead of using the actual equation, the square root of x, we're going to use a linear equation, which is very close to this equation right here. Okay, now, as I look at this value, square root of 1.03, okay, I notice that this is very close to the square root of 1. The answer to this question will be really close to the square root of 1, because this is just a little bit bigger than 1. So here's the concept. Here's what I'm going to do. I'm going to write a linear approximation for this function, wherever 1 is at. I'm going to come in here and I'm going to write a linear equation that goes right through that point at x equals 1. Okay? Now, why would I want to do something like this? Okay? Well, here's the idea. If I just go over a little bit to the right, if I only go over 0.03 to the right, is my answer on the actual function going to be very much different than the actual on the linear, on the value on the linear equation? There's not going to be very much difference. That's why they call it a linear approximation. We're going to approximate this value by taking and subbing 1.03 into a linear equation. And it's much faster to calculate things with linear equations than it is with more difficult equations. Okay? Now, what's the one drawback of doing a linear approximation? Well, if I stay really close, like in this case, if I stay really close to 1, this is going to give me a pretty good answer. But what happens as I get farther and farther away from 1? What happens to the difference between the line and the curve? Well, it gets to be bigger and bigger, doesn't it? So I really don't want to do this. If I'm trying to approximate y equals 10.03, well, I don't want to write the linear equation at 1. That's not going to do me a whole lot of good, because there's going to be too much of a difference in here. It's not going to be a very good approximation. So I need to pick a value that's fairly close to the actual value that I'm interested in. Okay? All right. So now my question is, how do we write this equation of the line? Okay? This is something we know how to do, because all this is just the equation of a tangent line, isn't it? Okay? All we care about is the equation of the tangent line at x equals 1. So let's go ahead and do that. Okay? At the point 1, what's the y coordinate? If I just take 1 and I sub it in here, what do I get? I get 1, right? Okay, square root of 1 is 1. So my ordered pair at this location is just 1, 1. Okay? The other thing that I need to be able to write the equation is the what? I have to know the slope. How do I get the slope from an equation? What concept do we use to get slopes? Derivatives, sure. Okay, so I need to take the derivative of this function, and then I need to sub in x equals 1, because that's the point that I care about. All right, so let's go ahead and calculate this. Now, we're not doing any dy dt's or anything like that. There's no time component involved here. We're just looking at how y and x are related to each other. Okay, so my derivative on the left side is just dy dx. What is the derivative of the square root of x? 1/2 x to the minus 1/2, sure. Okay, just no fancy stuff here. We're just doing normal derivatives now. Okay, if I sub in x equals 1, 1 to any power is what? 1 to any number is just 1, right? 1 to the 5th is 1, 1 to the 10th is 1. Well, 1 to the negative 1/2 is also 1. Okay, so my derivative, or my slope, is just 1/2 times 1, which is just 1/2. Okay, all right. So the equation of my line that I've got here for my linear approximation is y minus 1 equals 1/2 x minus 1. The 1 here and the 1 here, that came from our ordered pair, and then the 1/2 was our slope value. Okay? All right, now, if I want to make this approximation, if I want to know what is this value for 1.03, what's the last thing that I need to do in this linear approximation? Well, what's the x value that I care about here? I want to know the x value for 1.03, right? I'm looking for square root of some number, and the number that I'm looking for is 1.03. So all I need to do once I write the linear equation is just sub in 1.03 to the linear equation. Okay? And let's go ahead and do that. Okay, I went ahead and added the 1 over right away at the same time here. Okay, this is just 0.03. And the nice thing about these, you can do most of these in your head. What's half of what is half of this 0.03 that we've got here? Point what? Half of 3 would be 1.5, right? Okay, so this is just 0.015. If I add that to 1, my guess is that the y value for this answer should be really close to 1.015. Okay, now go ahead and try it on your calculator. Go ahead and punch in square root of 1.03. Let's just see what you get. I want to make a comparison here. You know, how good of an approximation was this? 1.0148. Okay, if we compare that to 1.015, is this a pretty good approximation? Yes, it's pretty good. And we knew it should be pretty good because we didn't get very far away from that point where we wrote the equation for. Okay? Now, like I said, this was a pretty basic example. If we're doing a square root function, we have a calculator. Would it be necessary to do all this work? Well, no. I mean, because we can just directly punch this in our calculator. Like I said, this concept is used for more advanced functions where it's not that easy to make those calculations. Okay? And so you can write a linear approximation, you come up with that result. Okay? So that's a linear approximation. Okay? Now, we can also look at this process through what's called a differential. Okay? So I want to solve this same problem using the concept of differential. Okay? And then I'll let you decide which one that you want to use when you get ready to do the test question that's related to it. Okay? All right. The differential looks like this. Okay? I still have my initial equation, y equals square root of x. Okay? I still pick a nice ordered pair that's really close to the value that I care about. You know, if I want to do 1.03, I pick x equals 1. I pick a nice number really close to it, something that I can get the y value from in my head. Just something really nice. Okay? All right, here's how differentials works. Okay? If I go through and take this derivative, just like I did a little bit ago, I get 1/2 x to the minus 1/2. Okay? The concept of differentials is this. Differentials says that you can take this rate of change over here and we can sort of split it apart. Okay? What I mean by splitting it apart is we can take this dx and we can multiply it across using cross multiplication. So if I rewrite it after doing that, I've got 1/2 x to the minus 1/2 times dx. All I did was just kind of multiply that. I split the derivative apart. I'm going to look at the change in y over here, and I'll look at the change in x over here. Okay, now let's look at some values to sub in here. You know, just like we did on the related rate problems, let's figure out what's the value of x and how much of a change in x did we have. Okay, all right. This is 1/2. What was the x value that we started out from? Well, we started out from x equals 1, didn't we? Okay, so I'm going to plug in 1. How much of a change in x do I need to have in order to be able to get over to the point that I care about? How much of a change do I need? 0.03, right? The same number as down here. I need to change from 1 to 1.03. So if I sub in dx as 0.03, okay, if we go through and do this calculation, okay, what do I come up with? What is this number? Okay, well this is just a 1 right here. Half of 0.03, we already did that a little bit ago, right? It was 0.015. Okay? This is telling me how much my y value needs to change in this problem. My y value needs to change by 0.015. where was the y value at when I began? It was at 1. So what's the final answer then? If it's at 1 and it changes by this much, isn't it at 1.015? And that's the same answer we get down here. Okay? So I like differentials better just because they go a little bit faster. Writing the whole linear equation, I mean, that takes a little more time, but to me it's a little bit easier to understand that way. But differentials accomplishes the same thing, and to me it's a little faster. So that's why I'm going to try to push this method here, especially as we progress in the course. You know, after we come back from spring break, we're going to talk about this same concept of differentials with not just 2 variables, but with 3 variables. And it works a lot nicer to write an equation, or to not write the equation and just do the differentials. Okay? All right. So let's look at another example here of differentials. Okay. What if we take this equation, y equals 2x squared minus 5x. If we let x be negative 2, so we're going to start at negative 2, and we're going to let the value of x change by 0.02. Now let's just do 0.2. Okay. We want to find this particular value. Okay, let's use differentials to find this. Okay. My first question is, well, where did we start? Okay. If I have x equals negative 2, let's go ahead and turn this into an ordered pair. What's the y coordinate for where I started? Okay, well this would be a 4. 4 times 2 is 8. Negative 2 in here would be a 10. 8 plus 10, it looks like it's 18. Okay, so we punch this in. I'm starting at 18. Okay, now what I've got to figure out is how much did my y value change? You know, I need to figure out what dy is so that I can change it from that 18. Okay, all right, let's use differentials to solve this. Okay, well, we take our normal derivative. Derivative of the left side is just dy dx. Okay, what's a derivative over here? Well, just simply 4x minus 5. Okay, now I want to go in and I want to multiply this dx across. So I have dy equals 4x minus 5 times dx. Okay, all right, what is the x value that I care about? Negative 2. Okay, so I sub in negative 2. 4 times negative 2 minus 5. And then how much is the x value changing? Dx is changing by 0.2, right? Okay. In other words, I'm letting it start at negative 2, and by the time it changes, it will be at negative 1.8. It's going to change by that much. Okay. All right, and now from here, I just do my calculation. Let's see, this is negative 8 minus 5, so that's negative 13 times 0.2, which is the same thing as dividing by 5. Negative 13 divided by 5 is negative 2.6. Okay, thank you. All right, so this is telling me how much the y coordinate needs to change if I let the x coordinate change by 0.2. Okay, so then what's my final answer here? What's the actual y value that we want? Okay, yeah, I take where I started, 18, and I subtract 2.6. And so this answer is 15.4. So we're estimating, or we're approximating, that on this function, okay, if I sub in x equals negative 1.8, you know, if I change my y or my x coordinate by 0.2, I'm guessing that the y value is really close to 15.4. Okay, and did anybody punch it in? What is the actual y value? Okay, take negative 1.8 and sub it into this function. Let's see what it is. Okay, I just want to get an idea of how close it is to 15.4. Okay, and then the question becomes, is that close enough for what we're trying to do? And probably the answer is yes. Okay, this is about 15.5 and this is about 15.4. and so that's okay. Big advantage of this, notice I didn't use any calculator. I did this whole thing in my head, okay? Could I sub in negative 1.8 in my head? Well, it'd take a little longer, okay? So the big advantage here, computer runtimes are much faster with linear equations. It doesn't take a computer long to calculate something if you sub it into a linear equation. But when you get higher powers involved, the speed of how fast it can compute these things becomes less pretty quickly. Okay? If you wanted to calculate something to the 1,000th power, it would take it a long time to multiply it by that number 1,000 times. But if I write a linear approximation, the runtime is very quick. Okay? And so this is used in a lot of computer programming type situations. Okay. All right, that'll work here for today. We'll see you next time.